Hello, everybody. Happy Monday to you. Hopefully, you all had a wonderful weekend. I'm recording this on Friday and I'm looking outside and it is just lovely. I cannot wait to get out and enjoy mowing my lawn. I'm actually really looking forward to it. This is my first time doing it this year and it looks like a glorious day to do that. So, I'm not sure what the rest of the weather is going to be like this weekend, but if it's half as good as today, hopefully, you had a chance to enjoy it at least a little bit. We are going to be moving on from circles today. I actually thought we were going to do a little bit more, but as we're mapping out the rest of the year, well, there's really not all that much of it left. So we'll see. I may introduce some different types of circle questions as we review circles, but we are going to move on to start ellipses today. Um, and then we'll also do hyperbolas before the end of the year. And then we'll have to do a little bit of review, make sure you guys are ready. We've got one more test coming up at the end of the year, which, by the way, is going to happen on the 29th. The test will be on the 29th. That is our last day. If you have makeup work to turn in, or if you're, I don't know, sick on the 29th or something like that and need to make up the test, you'll have the opportunity to do that the week after. But most of you, I'm sure, will be done on the 29th. Um, Ellipses, and I'm kind of waffling right now how much I should spend talking about them. I'm going to give you one brief definition of an ellipse, and that is, unlike a circle, that every point on the circle is the same distance from a center. The center of this ellipse that you're looking at on your screen right now is at 0, 0. And so obviously the distance, if I go straight up, is only 5. The distance to a point on the ellipse, if I go either to the left or the right, is 9. So it's definitely different. It turns out that one of the definitions of an ellipse, is actually a set of all points that have the property where the sum of the distances to the two foci are the same. And for the ellipse you're looking at right now, I'm going to have to draw in, I believe, one of the foci. By the way, foci is just plural of focus, F-O-C-I. I have one focus over there. I have two foci inside of this ellipse. And so my definition of this ellipse is that every point on this ellipse obviously is not the same distance from a center, but if I take the sum of this segment and that segment, no matter where I do that on this ellipse, this distance plus that distance would be the same as this distance plus that distance. And so that's a definition of an ellipse that, well, frankly, if we had a few more days, we could spend more time looking at that and seeing how that gives us the equation. But instead of doing that, what we have chosen to do is just look at the general form of an ellipse and see where that comes from and think of it in terms of transformations and scaling. So we'll get to that. Right now, you're looking at something that is notes/homework. This is a PDF that's attached to your homework assignment. We're looking at the first page that I'm going to be using as my notes for the day. And then the assignment is the second page of this. So this is the part that you'll be doing as your homework assignment. We'll do the front page as your notes. Basically, I'll just be going through this and filling everything in and making sure that we know what's going on. And so part A is just asking for the length of each axis. In an ellipse, you've got a major axis and a minor axis. The major one is just the longer of the two. In this case, for this ellipse, it is the horizontal axis. And we're going all the way from -9 to +9. So my major axis, my horizontal axis, has a length of 18. And the vertical axis that goes from y equals -5 to y equals +5 has a length of 10. So that's the length of each of the axes. The center of this one is at 0, 0. We'll see some that are not centered at the origin. But this one's just making sure that we see, even though the axis is 18, the distance from the center to a point that's on the ellipse is half of that, or 9. And then vertically, again, the axis has a length of 10, but the distance from a point on the minor axis to the origin is half of that, or 5. And so for points that are on the ellipse, this is similar to what we did with circles. We could either go straight up, straight down, straight left, or straight right to get these 4 points. And so one of the possibilities is 9, 0, and you'll have to pardon me as I write using my mouse. So 9, 0, and negative 9, 0, those cover the points on the horizontal axis, or the major axis in this case. And then if I go straight up, I've got 0, 5, or straight down to get to the point 0, negative 5. And obviously there's a lot more points than those, but those are the 4 that are the easiest to find: straight up, straight down, straight left, and straight right. So this is an equation for this ellipse, the one that we've been looking at. And as you look at these numbers, x squared over 81, you might have a guess as to where that 81 is coming from, plus y squared over 25. And if you thought you knew where the 81 came from, you probably know where the 25 comes from as well. We'll get to that in just a moment. But this question is just asking to verify that one of these points is on the ellipse. It'll work for all 4 of them, but I'm just going to choose 0, negative 5 as the one that I plug in. Plug in 0 in place of x, 0 over 81, plus negative 5 squared. Negative 5 squared, of course, is 25. So I've got 25 over 25, which is 1. And of course, this is equal to 1. This fraction is equal to 1. This fraction is equal to 0. And honors functions and trig class, 1 plus 0 is equal to 1. So it looks like that one works, and it would work for all 4 of those. This ellipse is a scale change image of the unit circle that we all know and love at this point in the year. It's asking by what factor was it stretched in the horizontal direction? Well, the unit circle is a circle with the radius of 1 centered at the origin. There's the unit circle. And so horizontally, it's been stretched out by a factor of 9. The horizontal diameter is going from a distance of 2 to the distance all the way across. This is 18. So it is 9 times as big. So my scale factor is 9. Vertically, the scale factor is 5. And then another ellipse is an image of the unit circle that's been stretched by a factor of 6 in the horizontal direction and 8 in the vertical direction, and they want an equation for that. Well, as I alluded to before, you probably figured out that these distances, the amount of the horizontal stretch is squared, and that shows up in the denominator of the x term of my equation, and then the vertical stretch, the factor of 5, is squared in the denominator. So if I were to stretch the unit circle by a factor of 6 in the horizontal, x squared over 36 is going to accomplish that. A factor of 8 in the vertical, 8 squared is 64. And so if you graphed this, if you went on Desmos and graphed this, or if you switched it around into function forms you could graph on your calculator, this equation would lead to an ellipse that is 12 units wide and 16 units tall, stretched out by a factor of 6 and 8 horizontally and vertically. All right, moving along. Let's see. Here we go. Question 2, they want me to plot an ellipse that is centered at the origin with a vertical axis of 14. So not stretched by a factor of 14, but the vertical axis is 14. So stretching all the way from +7 down to -7. And I apologize, this graph, there's little tiny numbers. On the vertical axis, it's counting off by 2s. On the horizontal axis, it's counting by 5s. So hopefully you can see that. The horizontal axis is 6, 1, 2, 3 to the right, and 1, 2, 3 to the left. And I'm sure most of you will do a better job of this than I did, or what I'm doing. But to draw this ellipse, I'll think of it similar to when I did circles, where it's got to be vertical at the left and right endpoint, and it's got to be horizontal. Ooh, that's not, well, it's not terrible, but it's not great. Got a little bit of a lumpy ellipse over on that side. But actually, I feel not too bad about that one. The equation for the ellipse, well, this distance right here, the horizontal distance is 3, the distance from the center, half of the axes, or the length of the axis. And so x squared over 9 coming from 3 squared. And then y, the vertical distance from the center to a point on the ellipse, is a distance of 7. And so I'll have y squared over 49, or 7 squared. So this is the equation for this ellipse. The scale change, and this is a notation, it may be a new notation for you, but that's why I'm explaining it right now. This notation, S with a subscript of 3, 7, this is saying that we've got a size change, S standing for size change, and horizontally, a scale factor of 3, vertically, a scale factor of 7. And we've already seen this, but I'll put it down here to answer this question. These numbers show up in the equation in the form of the horizontal factor, shows up as the denominator, 9, for the term with the x, and the vertical scale factor squared is 49, which shows up in the denominator of the y component. These things are showing up in the equation in the respective denominators. All right, so if I say I want an equation for a unit circle under a scale factor horizontally of 5, that puts a 25 in the denominator of the x term, and 2, we'll put 2 squared in the denominator of the y term, excuse me. And so this equation describes an ellipse that would be stretched out by a factor of 5 horizontally and stretched by a factor of 2 vertically. And then finally, this notation, this uppercase T, is talking about a translation. We've seen this with circles. The general form is actually looking kind of similar to what our circle general form was. The scale factor horizontally of a factor of 2 means we'll have 2 squared or 4 in the denominator of the x term. Scale factor of 6, we'll put a 36 as the 6 squared, the scale factor squared of the y term. And then as we saw with circles, if I want a horizontal translation by distance of 11 units to the right, we'll put that in as the amount that's subtracted from the x term. And then a vertical translation by -2, or moving down 2 units. I'm going to make this a plus y plus 2, which is the same as y minus -2. This would be the equation for an ellipse that is stretched horizontally by a factor of 2, vertically by a factor of 6, and then to the right by 11 and down 2. So lots of transformations happening. We'll do one more general one here. So you've got a formula for this. Scale factor by a factor of a horizontally and b vertically. We'll just take whatever that scale factor is and square it and throw it in the denominator. And then the hk is the same h and k we saw with the circle. If I wanted to move h to the right, we'll do x minus h. If I wanted to move up by k, we'll put y minus k. And so the values of these numbers tell you how far the ellipse, the center of the ellipse, is moved up, down, left, or right. And I'm just going to take a quick look at the assignment and see if there's anything here. All the notations we've talked about. And yep, I think we should be okay. So finish up the rest of this as your assignment that's due on Tuesday. And we'll reconvene then. We'll have a little bit more to do with ellipses before we move on to the next topic. So have a great day. Let me know if you got any questions or comments, and we will see you later. Bye-bye.